Hi, friends. If you are live streaming in, we are slightly delayed, so hang tight. Our TA should be there in a minute, and then we'll get started. Hi, friends. If you are live streaming in, we are
Professor.
I think, can you hear me okay?
Yeah. Just so you know, the TA is not here.
The TA didn't show up, none of them?
No. I don't know where they are.
Okay. books. I'm not sure where they went either. Are there students there?
Say again?
Are there
Yeah.
students? Okay. Well, we'll get started and, and then hopefully the TA will show up. Maybe they're just running behind. All right. Let me get this going. All right. Okay, so hello, good morning, everybody. Welcome to our very last class. You've made it to the end of the term. This is very exciting. So a couple quick announcements. As a reminder, we have our Chapter 5 quiz tomorrow, and we have a mini quiz tomorrow. So make sure that you complete both of those. I obviously am going to recommend that you do the mini quiz prior to the chapter quiz. Once you have that completed, the only thing that is left is if you are going to be doing any homework for half credit, that will be due on Thursday. The plan is that on Friday, I will process the homework grades and add those to Moodle, and you will be able to see what your final grade for the class is, which will help you decide whether or not you want to take the optional final. So at some point on Friday, probably later on Friday, you will be able to see your final average for the class and make your decision accordingly. And we'll send out an email about that and how that works. But, we are very, very close to the end. So that's what's going on there. Yeah, so we have our last section of Chapter 5 today, and it's called the Fundamental Calculus. And once we have that, we just are going to go from there. So if you are taking Math 128, you will do a little tiny bit of the stuff that we're doing with 5.5 to sort of kick off Math 128. And so that's sort of the overlapping link between the two classes. So I'm going to go ahead and switch here to the doc cam. Okay. And so we're going to talk about total change and the fundamental theorem of calculus. So what does that mean? So we've been talking about this word total. What is the total change of the original function? And we've been using area under the curve to talk about this. So the fundamental theorem of calculus is a pretty important theorem because for a long time, the Newton and Leibniz, who are sort of looking at calculus and area under the curve and things like this, was a whole field of calculus. And then there was also what's called integral calculus. And this is one of the starting theorems that begins to link sort of what we now look at as Calc 1 and Calc 2. So what does the fundamental theorem say? So suppose that f, capital F prime of x, is a continuous function on a, b, so on some interval, then the definite integral from a to b, which is what we've been studying, so the area under the curve between a and b, right? We know it's going to tell us the total change of the original function. This is going to be equal to f of b minus f of a. Now notice this is not f prime, so this is the original function. So what is that telling us? So let's think about position, right? We started talking about distance. If we were to find the area under a velocity curve and say that that area is 40 feet, right? Then we know that the original function changed by 40 feet. What this theorem is saying is if we had the original function, position, and we measured the ending position minus the starting position, we would also get 40 feet, right? And that seems really, really silly. Like, of course, if we had the original function, we could just subtract the starting point and the ending point and find the change of this function, right? But even though we can do it, what's happening here is we were working under the premise that we didn't have the original function, right? We had the derivative function, and that's why we had to use area under the curve. So now that we've linked this to the original function, the work that happens in calculus 2 is how do we find the original function, right? If we have the derivative, how do we algebraically go back to the original function? So we are not going to do that in this class. We're not going to find what's called antiderivatives. But we're going to use this idea of the fundamental theorem that these represent the same thing to help us understand the value of the original function at one of these points. Okay, that's sort of our goal here. So let's see how this works. Let's see how we set this up. Let's see what this means for us in context. Okay, so example 1, suppose ice is forming on a pond at a rate of dy dt equals the square root of t over 2 inches per hour. Okay, so this is the rate at which the ice is forming, and our variables here are y and t. If y represents the thickness of the ice in inches at time t in hours since the ice started forming, okay, so that means that the original function is y of t, right? So we're plugging in a time and we get out how thick the ice is. We want to estimate the thickness of the ice after 5 hours, okay? So we know the rate at which the ice is changing. We know the variables we want to use to talk about this, and we want to find the area under the curve to help us figure out how thick the ice is. So what I would like you to do is think about how we would set this up using what we already know from previous stuff. We can get to the right answer. And then when we go through it together, we're going to talk about how we can set it up in this form using the fundamental theorem to come to the same conclusion, but to help illustrate why we would use the fundamental theorem. Okay, so I want you to take 2 minutes, think about how we're going to use this rate, what are going to be the bounds of our integral, how do we find it, what are the units going to be, we've talked about units, and then we'll go through it together. Okay, take about 30 more seconds. All right. So intuitively, from what we've learned before, we know we want to integrate our rate, and our bounds here are going to be 0 to 5. So there's something happening in the background, an assumption that we're making that will become more explicit when we write everything out. So if we integrate our function from 0 to 5, we have the square root of t over 2 dt, right? That's going to tell us the total change in the thickness of the ice, okay? Now, the fundamental theorem says that this is the same as if we had the original function at hour 5 minus the original function at hour 0, right? And what we are trying to find here is the thickness of the ice after 5 hours. So this is the value that we are trying to compute. So what that means is that we need to take y of 0, so the thickness of the ice at time 0, and bring it to the other side, right? If we do that, we get y of 5 equals y of 0 plus the integral from 0 to 5 square root of t over 2 dt. Okay, so all I did is I took this term and I added it to the other side, and then I kind of switched what is on the equals. Now, if we calculate this definite integral in our calculator, what do we get? So if we plug that in, we are going to get 3.726. Okay, so let's talk about the units of this. So the units of the rate are in inches per hour. So then we know the independent units are in hours. Hours will cancel. So we get 3.726 inches. Okay, what we are assuming here, and we want to make more explicit, is that y of 0, the thickness of the ice at time 0, is 0 inches. Okay, so if we were to just compute the definite integral, this assumption is in the background that we were starting with 0 inches, which is a completely reasonable assumption in this case, right? We know that the definite integral tells us the total change in the number of inches. And given this context, it's pretty normal to assume that we start with 0 inches because it's when it starts forming, which means that at time equals 0, we didn't have any inches. So when we use the fundamental theorem, it makes this more explicit. And the reason why we want to do this is because when we start having initial information that's not 0, we know and remember to add it on to the total change. And we did this in context a little bit. A couple classes ago, we said, hey, if the original is this amount, then what? And we had to go back and add it on. But this is how we formalize it. So we're going to be setting up integrals today using the fundamental theorem. We're going to be looking at things like what is the initial condition if there is one, and then using that to solve for either the original function at time B or the original function at time A. And we're just including all the work we've been doing with integrals. So here, the time 5, the inches will be 3.726 because if you add 0, it's still 3.726. Okay, so we're not doing too much more than we were doing before, but now we're setting it up more formally. So let's look at the next one. I don't know why I printed these so close. There's not a whole lot of space on this one, but maybe we'll write on the index card. Here we go. So a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room when time equals 0. The coffee's temperature is changing at a rate of R of t equals -7 times 0.9 to the t degrees Celsius per minute with t in minutes. Estimate the coffee's temperature when t equals 10. So there's a lot of numbers in this problem, and we have to figure out which ones are relevant, which ones are not relevant, how we might set this up. So what I'd like you to try to do is set up how we might solve this problem using the fundamental theorem of calculus. So what are we integrating? What are the bounds, right? How do we write this as the fundamental theorem? And which of these values do we know from the problem, right? So we have to think about how to put all this information together to solve this problem. So take 2 minutes, and then we will go through it together. take about 30 more seconds. All right. So here we see that the rate is -7 times 0.9 to the t. Since our variable is t, we're going to use dt. So we have to figure out what goes on the bounds. So we're interested in what's happening from time equals 0 to time equals 10. And so since our rate is in degrees per minute, right, then that means our independent variable is minutes. So it's minutes that we are interested in putting on our bounds. So we're interested in this change of temperature during the first 10 minutes. And so here, if the rate at which we are changing is little r of t, we need to come up with some representation for the original function. There's a lot of ways you can do this, and there's a lot of flexibility because we're not told what to call the original function, but I'm going to call it capital R of t, so r of 10 minus r of 0, because in math we'll often use capitals to represent the original function and then the lowercase to represent the derivative function if it's not, you know, a prime. So this represents the original function, which is the temperature of the coffee. We want to know from this particular setup the temperature when time equals 10. So this is the value we're interested in. So again, we can add this r of 0 over to the other side. So we have r of 0 plus the integral from 0 to 10, -7, 0.9 to the t, dt equals r of 10, the value that we're interested in. Now, the definite integral, we're going to plug into the calculator, right? We're going to plug that in to get that value. And then we have to reason through what r of 0 is. So let's do the definite integral first. So when you plug this into the calculator, you're going to get -43.27. And now let's talk about units. So the units of the rate were in degrees per minute. The independent values were in minutes, so those are going to cancel. So this is -43.27 degrees. And remember, this is in degrees Celsius. Okay. Now, r of 0 is the temperature at time equals 0. So there's two different temperatures presented in this problem. It says a cup of coffee at 90 degrees Celsius is put into a 20 degrees Celsius room. So we have to figure out which one of these values are we talking about. Well, we're talking about the rate of change of the coffee's temperature, not the room's temperature. So r of 0 is 90 degrees. So we have 90 degrees plus -43.27 degrees. So that's how much the temperature changed. And when we add those together, we get 46.73 degrees Celsius. So the temperature after 10 minutes is 46.73 degrees. Okay. Now we could certainly reason through this without setting it up through the fundamental theorem of calculus, but this is more formal, and we definitely ask questions to make sure you're setting it up this way. But what we're really doing is we're taking the change of the function and adding it to the initial amount, which is stuff we've done before, but now we're just formalizing it. Okay. All right, so let's look at our next problem. I'll leave this up here in case we still want to see it. Let's see. Okay. Here we're looking at a graph. So the figure below shows the rate of change of the quantity of water in a water tower in liters per day during the month of April. If the tower had 12,000 liters of water in it on April 1st, estimate the quantity of water in the tower on April 30th, right? So we're trying to think about the rate of change How do we find that on a graph? Remember, we're going to be using area under the curve to think about this. And we want to think about how we can set this up using the fundamental theorem as well as using the information from the graph. So what I would like you to do is to try to set up what we are trying to find using the fundamental theorem, and then figuring out all the pieces and the information we can get from the graph. I do want to point out that the 0 line is here, sort of in the middle. We have 50, 100, 150, and then -50, -100. So the 0 line is sort of in the middle. It's not at the bottom. Okay. So we're just approximating. We're just, you know, doing your best. There's a couple different ways you can approximate. We may not all get the same exact answer, but we should get something in the same ballpark. Okay. So I'm going to need about 2.5 minutes. See what you can approximate here, and then we will go through it together. All right, take about 30 more seconds. All right. So let's start by setting up something in terms of the fundamental theorem that represents what we're trying to find here. Okay, so we don't have a particular function, like an algebraic function that we're working with here. We just have this graph. So let's call the function that we're going to look under little f of t. You can call it whatever you want. I just need to call it something so I can set up my integral. So I'm interested in the area under the curve from day 0 to day 30, right? I'm looking for the change over the 30 days of the amount of water in this water tower. And I know from the fundamental theorem that that would be the amount of water on day 30 minus the amount of water on day 0. Okay. So again, I'm using capitals to represent original functions and lowercase values to represent the rate. Again, you don't have to call this f of t. You could call it, you know, w of t for water or anything like that, but we need something to call it to set up an integral. So what we're looking for here is the amount of water on day 30. So we want f of 30. So again, we can add the original amount over to the other side. So we have the amount of water on day 30 is equal to f of 0 plus the integral from 0 to 30 f of t dt. Now, conceptually, this should make sense because what this is saying is the amount of water on day 30 is equal to the initial amount of water plus the amount of water that has changed, right? Which is what we've been doing when we've been doing prior problems. So the question really is, which numbers do we know? Which numbers do we have to find out, right? As we sort of move along. So f of 30 is the one that we're trying to find. So we don't know that yet. F of 0 is the initial amount of water. So if we go back to the original problem, we see that the tower started with 12,000 liters of water. So we have 12,000 plus, and now this is where we need to do some work with our graph, right? So we want to find the area under the curve from 0 to 30 to figure out how much our water changed. And like I said, there are many, many, many different ways you can estimate the area under the curve and get something similar. I'm going to tell you how I approached it, and then we'll talk through some reasonable alternatives here. So one thing we have to remember is that area above the curve is positive and area below the curve is negative. So this first chunk, right, up until day 12, this is all negative area. And when I look at this, this looks pretty close to a triangle for me. So I'm going to treat this as a triangle to approximate this area that's going to be negative. So for a triangle, I'm going to be doing 1/2 base. My base is 12 times height, which is negative 50. Remember, when we're talking about this in the context of calculus, we're using these y values, which are negative, which allows us to have this negative area. And that's going to give me, let's see, negative 300. So that means that I'm losing 300 liters of water over the first 12 days. But then I become positive. Now, the positive for me doesn't look like a triangle because we sort of cut off right here. So I'm going to approach this in a slightly different way for the positive area. Okay, and this is what I'm going to do. So first, I'm going to approximate the area of one sort of box, right? So here I can see the height of one box is 50 and the width of one box is 6, right? So I'm going to do 6 times 50, which gives me 300. So the area of any one of these little boxes is 300. Now I'm going to try to approximate the number of boxes that are underneath the curve from 12 to 30. So this is the area that I'm trying to figure out here. So what I see is I have a full box here, 2, 3, 4. So I have 4 full boxes, right? And then I have these 2 kind of make a box and these 2 kind of make a box, right? So I'm going to pair these together to make box 5, and I'm going to pair these together to make box 6. Okay, so it looks like I have approximately 6 boxes here, which means I'm going to do 6 times 300 because each box is worth 300. So when I multiply those together, 6 times 300, I get an approximation of 1,800 for the area above the curve. Now, you could certainly try to jam in like a triangle and a rectangle. You should be in the same ballpark, somewhere between 1,500 and 2,000, right, is reasonable. So now we have to consider both of these together. The total change is adding up the negative area and the positive area. So positive 1,800 minus 300 is going to give me 1,500 for the total change. So the area under the curve is going to be 1,500. So now I have the original 12,000 plus I've increased by 1,500, which means that the amount of water after 30 days will be 13,500. Okay, so that's how we set everything up. That's how we then calculate each piece and how we put it all together at the end. So being able to do this and set it up in this way is important. It's more formal than what we were doing before, but we can also reason through why this would be the same as the types of things that we were doing previously to this. Okay. So the next function is also a graphing problem. And it's interesting because what we're going to do is we're going to use the graph of the derivative to help us understand the behavior and values of an original function. So this sort of goes on to the next page. So we're given the graph of f prime of x. Okay, so it's this graph up here. I'm just gonna trace this. It's a little bit lighter on the screen than it is on my paper. Okay. In addition, we know that f of 0 equals 2. We want to use this information with the graph to find the following tables of values for f of x. Okay. And it says make sure you mathematically justify how you got your answer, which just means, set up the fundamental theorem, integrals, and show your work. So let's talk about the first one together, and then I'm going to have you work on the rest of the table. So what are the important pieces here? This is the graph of f prime of x, and we're using it to find the values of f of x, which is the original function. So if we were to set this up using the fundamental theorem of calculus, we would want to start by setting up the integral from 0 to 1, right? So the integral from 0 to 1 of f prime of x dx will equal f of 1 minus f of 0, right? Well, what are we trying to find? We're trying to find f of 1, right? So we would add that over. So we have f of 1 equals f of 0 plus the integral from 0 to 1 f prime of x dx. Okay. Well, f of 0 is the value that was given to us in the problem. So that's 2. Plus, now we need to add on how much we change from 0 to 1. Well, from 0 to 1, we have this little triangle here, right? So we're going to do 1/2 base times height. My base is 1 unit long, and my height is going to be -1. We are below the x-axis. So that means we get -1/2. So you can write that as a decimal, or you can write it as a fraction, whichever you prefer. But we have 2 minus 1/2, which gives me a value of 1.5. Okay, so we're going to do that for the rest of the table. So the next integral you'll set up is the integral from 1 to 2. Use the fundamental theorem to rearrange, find area under the curve, right? And you're going to do that for the whole entire table. And I just want to point out that once you get to part 4 here, that from 4 to 5 and 5 to 6, that is above the x-axis. So that is positive area, right? Before 4, it's all negative area. So I'm going to give you about 3 minutes to try to fill out that table. Set up the definite integrals if you can, just for good practice. And then we'll go through and we'll look at the areas together in about 2.5 to 3 minutes. Take about 30 more seconds. All right. So when we are calculating, what is happening in the background is that, say we're going from 1 to 2. We're taking the value at 1, right? And we're adding on the change from 1 to 2. So let's see how much it changes from 1 to 2. From 1 to 2, we have this little rectangle with a base of 1, a height of -1. So we're changing by -1 units. So 1.5 minus 1 is going to give us a value of 0.5. Now, to go from 2 to 3, we're going to take the value at 2 and add on the change from 2 to 3. Again, that's going to be a rectangle with a base of 1 and a height of -1. So we're going to subtract another 1 from that value. So -0.5 now, because 0.5 minus 1 is -0.5. And then from 3 to 4, we again have a triangle. So we have 1/2 base times height. So again, the base is 1, the height is -1, and then we have this -1/2. So we have -1/2 minus 1/2. So now we have a value of -1. To go from 4 to 5, we now cross over. We're getting positive area. Okay, so we're going to do 1/2 base times height, but the base is 1 and the height is +1. So now we're going to add 1/2. So -1 plus 1/2 is -0.5. We're getting less negative. And then finally, from 5 to 6, we see that we have a rectangle, base of 1, height of 1. So we're going to add 1. So -0.5 plus 1 is going to give me +0.5. So when we do this, we are literally getting values on the original function. So we could plot this to find a rough graph of what the original function looks like. The only reason that we are able to do this is because we have this initial value. If we did not have some value on the original function, we would not be able to get other values, right? Because it's all in context of one value. And then we're evaluating how much things change based on that starting point, okay? So that's how we're using the derivative. We've done work like this before, not quite to this application, but when we talk about the area under the curve and we talk about how much the original function changes, that also gives us an idea of the values of the original function. Okay, so now that we've sort of practiced with area under the curve on a graph a couple times, we have an application that's pretty standard in physics classes that use calculus-based physics classes. So we're gonna try to put things together and see what we can come up with to talk about a moving object. So we have the velocity of some sort of moving object given in this graph below. So again, this is the 0 line. This is +5, this is -5, and you can kind of see where things cross over at 4, and then again at 16. And this is time, right, in seconds. So over a 30-second period, and the velocity you can see is labeled here in meters per second. So we want to A, describe the motion of the object over the first 10 seconds. So again, we've talked about velocity before when we talked about like the house problem, like how far away you are from the house. So when something is positive, that means the position is increasing away from wherever you are. And when it's negative, that means we're coming back towards wherever you are. And so we want to talk about it in that context. When are we moving away? When are we moving back based on the first 10 seconds? And how much? So looking at that area to talk about it. Part B, what is the acceleration of the object during the first 8 seconds? So we know that acceleration is the derivative of velocity. So this is actually going back to our chapter 3 and 4 work. How do we talk about the derivative of this particular function over the first 8 seconds? So we need to think about it in that context. So we're not doing area under the curve. We're now thinking slopes again. Part C, during which times is the car accelerating and decelerating and constant? So again, we're thinking about the derivative of velocity here. We're kind of going in both directions on this. So thinking about when acceleration will be positive and when it'll be negative based on the derivative. And then part D, suppose that at time t equals 0, the object is at its home base. How far away from the home base is the object at time t equals 4 and time t equals 12? So we need to sort of evaluate what's happening, at time equals 4 and time equals 12 based on where we are in the picture and the area under the curve. So there's a lot of things going on here. Sometimes we're using area under the curve. Sometimes we're using derivatives, thinking about how we sort that out. I'm going to give you 3 minutes to try to work through some of this. Don't feel like you need to do these in order. If you feel comfortable with some of the questions and not others, definitely skip around. And then we will go back through it together and see how this all shakes out. So again, this is sort of chapter 3 through chapter 5 that would have to be applied here. All right, take about 30 more seconds. All right. So there's a lot going on in this problem. This really, like I said, ties into things we've been doing since chapter 3. So let's think about how we can answer these questions, evaluate things, and put it all together. So I think it's important to remember what we're looking at here. So when you have S of t, that's the position of a function, right? When you take the derivative of position, you get the velocity. And then when you take the derivative of that, so the second derivative of position, the first derivative of velocity, that's when you get acceleration. Okay. So here in part A, describe the motion of the object over the first 10 seconds. So we're really looking at how the position is changing. So we're talking about area under the curve. So remember, this is a graph of velocity. So to talk about the original function, we are looking at area under the curve. So if we consider what's happening over the first 10 seconds, we're going from time equals 0 to time equals 10. We see that part of it is above the x-axis and part of it is below the x-axis. So what we want to do is we want to describe when we are above and by how much and when we are below. So looking at the above part, right, I see that from time equals 0 to time equals 4, I'm above the x-axis. So that's the first chunk I'm going to consider. Time equals 0 to time equals 4. And I want to know what's happening there, right? So since it's positive, I'm going, we'll call it forward to represent one direction. And now we want to figure out how much we go forward. This is where we take the area to talk about the change in position. So when we look at the area here, we see that we have a triangle. Okay, so we can do 1/2 base times height to get this area. So 1/2, my base is 4 units long because I'm going from time equals 0 to time equals 4. And then my height is also 4 units high. So if you look at where we cross this axis, so 1/2 times 4 times 4 is going to give us 8. And here, if we think about the units are in meters per second times seconds. So 8 meters. So we go forward by 8 meters. And then from time equals 4 to time equals 10, we're going backwards or in the other direction. And now we need to figure out the area below the curve. So when I'm looking at the shape, I see a trapezoid. So if you're comfortable with areas of trapezoids, you can certainly do it that way. However, I'm going to split it up into a triangle and a rectangle. That's just sort of more comfortable for me. So the triangle here, so that's going to go until time equals 8. So I'm just going to label that. So from time equals 4 to time equals 8, my base is 4. And then my height, if I look at how far down it's going to go, it goes down to -4. So just the one before -5. So I've 1/2 times 4 times -4, which is going to give me -8 meters. But then I also need to consider what's happening from time 8 to time 10, right? So here, I have a rectangle that has a base of 2 from 8 to 10, and then a height of -4. So 2, -4 is going to give me another -8 meters. Okay, so that means that from time 4 to time 10, right, I went backwards by 16 meters. So you can either write it as backwards by 16 meters, you can put -16 meters, either is fine for now. We're just describing what has happened. Okay. So let's see what's next. What is the acceleration of the object during the first 8 seconds? Okay. So let's figure out where the first 8 seconds are. So the first 8 seconds, we've labeled the 8. That was helpful, right? The first 8 seconds means 0 to 8. So we're considering this line right here, which is helpful, right? We have a linear situation between 0 and 8. So if we're talking about the acceleration, okay, we're talking about the derivative of velocity. How do we find the derivative of a linear function? Well, the derivative is the slope of the tangent line. And if you have a linear function, it's the slope of the line. So we can get the acceleration by finding the slope of this line. Okay, so how do we find slope? For slope, we're going to change in y over change in x. So we have to pick 2 points on this line. So here, this is the point 0, 4, where we cross the axis here. And then we also have the point 4, 0 that we can use. We could also use 8, -4. I'm going to use 0, 4, and 4, 0, just because I think that will be easy to find the slope. You can pick any 2 points on the line. Okay. So the slope here, if we do the change in y, we're going to have 4 minus 0 over 0 minus 4, which is going to give me a slope of -1, which means the derivative of this function is -1. Okay, so we have the acceleration, which is going to be -1 meters per second squared. Okay, so the derivative, the velocity function, was in meters per second. And then we have to divide that by the independent units, which is another second. So it becomes -1 meters per second squared. Okay. For part C, we want to know when is the car accelerating, decelerating, and constant. So we're asking when is the derivative positive, negative, and 0. And so we're going to have accelerating whenever the derivative is positive, which means it's going in the upward direction, the velocity. It'll be decelerating when the velocity is going in the downward direction, and it'll be constant when it's just horizontal. Okay, so I'm going to write this down here. So we're going to be decelerating whenever we're going in the downward direction. So that looks like time equals 0 to time equals 8. And if I scan the rest of the graph, there's nowhere else that it's going in the downward direction. Okay, I'm going to be accelerating whenever I'm going in the upward direction. So that looks like that happens from 12 to 15. And again, from 20 until 24. Okay. And then last but not least, we're going to be constant whenever we have a horizontal line, which looks like 8 to 12. And then again, from 16 to 20. Oh, this should have been 16 up here. So for accelerating, that went from 12 to 16. I had written 15, but I see now that it actually goes all the way up to 16. So I adjusted that accordingly. So that's what we're looking at for part C. We're using the derivative, which again goes back to chapter 3 and 4. For part D, It says, suppose at a time equals 0, the object that's home base. How far away from home is the object at time equals 4 and time equals 12? So at time equals 4, we've actually already calculated that area, right, from part A. So that means at time equals 4, we're going to be 8 meters from home base, right? And now what about time equals 12? So time equals 12 is a little bit trickier. So let's draw a little bit of a picture here like we did with the other home base. So time equals 4. We've gone 8 meters away. And then after time equals 4, we turn around and we're going back in the other direction, right? So from time equals 4 to time equals 10, we go 16 in the other direction, right? We already did that in part A. But then we have to add on this extra leg from 10 to 12, right? So we go even further away, where from time 10 to time 12, we also are going in the away from home direction to the left in my picture. So here I have a base of 2, a height of -4. So that's another additional 8 meters to get to time equals 12. So if I add another 8 meters here, I have 24 meters. So depending on how I'm asked this question, you know, if you think about where I am at time equals 12, well, I'm not 24 meters away from the house. I'm 24 meters away from where I turned around, and I'm 16 meters away from the house. So it depends on how the question's asked, but if you draw a chart like this, it'll help you sort of see where this object is at any point in time, okay? So when you're talking about going towards and away something in a physics context, it's usually helpful to draw this type of picture. Okay, we're running out of time. All right, we gotta hustle to the next problem to make sure we get this last application in. Okay, so example 6. So one of the ways that this comes up pretty regularly, this idea of the fundamental theorem of calculus, is in the context of economics, specifically with cost. So the relationship of marginal cost and fixed cost is really prevalent using the fundamental theorem of calculus. And so when we talk about cost here, and we talk about integrating marginal cost, that's going to tell us the change of the total cost, right? So this is how we would rewrite the fundamental theorem to represent what we would be doing with something like marginal cost. Typically, when we're talking about marginal cost, your A equals 0, because we're talking about the total cost to produce some number of items, which assumes that we always start with 0. And as a reminder, C of 0, right? If you have cost at 0, that was called the fixed costs. Okay, which means that when we're looking for total cost, right, we're going to be looking for C of B, right, which is what we've been doing with F's in the other problem, but we can add this term over, which is typically going to be fixed cost. So fixed plus the integral from 0 to B, C prime of Q, dQ. So when we're dealing with what's the total cost to make some number of products, we're taking the fixed cost and adding on the change of cost to get that total cost, okay? So let's look at this example here. We'll see what we can shake out. There is another example after this that we likely won't get to, so you can watch that on the video. But this one will help us sort of understand quite a bit of it. So here in economics, we call the derivative of cost function the marginal cost. Suppose that for marginal cost, we have this graph below. So this is the graph of marginal cost. So part A, set up an integral to represent the total cost to produce 150 items of this product. Part B, use the graph to estimate the total cost to produce 150 items of this product. Part C, suppose now that there's an additional fixed cost of $1,000 to produce this item. What is your new cost to produce 150 items? D, suppose that you can sell this item for $25, write an equation to represent the revenue function and find the total revenue for selling 150 items. And then part E, find the total profit earned by making and selling 150 of this item. So part D and E sort of go back to what we were doing with economics before, but A, B, and C help us sort of understand how we can do the work we've been doing in the context of economics. So I'm going to give you 3 minutes. See what you can figure out here. Again, we're going to be approximating, so just do your best. It doesn't have to be perfect. We want to get a rough estimate of what's happening at 150, and then see what you can do to answer the rest of the questions, and then we will go through it together. Take about 30 more seconds. All right. So part A asks us to set up an integral to represent the total cost to produce 150 items of this product. So if we look at how we set this up to find any particular cost, we're going to have fixed cost plus the area under the marginal cost curve here. So we'd have something like this where 150 is what we're looking for. So that shows up here and at the top of our integral. For part B, it says use the graph to estimate the total cost to produce 150 items. So there's a lot of ways we can do this. We can do the block method where we approximate one block and then count the number of blocks. We can try to fit in shapes we know. Either is fine. So what I did is I went out to 150 and I split this up into a rectangle and a triangle, right? So 150, so this up here is right around 15. right? And so if you used a different approximation method, that's totally fine. You should still get something in the same ballpark as me. So for my rectangle, my base is 150 and my height is 6. So when I multiply 6 times 150, I get 900 for my rectangle. And then for my triangle, I'm going to do 1/2 base times height. My base is 100. And my height here, I approximated to be 15. So this is 12, 14, 16. And to me, that looked like it was right in between. So I did 1/2 times 15 times 100, because you can see the base stops here, which is roughly 100. So I multiplied those together, and my area for my triangle was about 450. So 450. So I have 450 plus 900. If I add those up, I get 1350. So the total change that I approximated for part B was $1,350 as the change in cost to produce 150 items. Part C says, suppose that there's an additional fixed cost of $1,000. So what's your new cost? So fixed cost is added to the total change. So we're going to add 1,000 to 1,350. So we get 2,350 for part C. Part D wants us to set a revenue equation that represents if we're selling these for $25 a piece. So revenue would be 25Q. And we want the revenue if we were to sell 150 of them. So we would have $25 a piece times we sold 150. So our revenue would be $3,750 if we could sell this item for $25 a piece. And then finally, part E, the total profit by making and selling. Well, we know that profit would be revenue minus cost. So revenue at 150 minus cost at 150. We said the revenue was $37.50 and the cost was $23.50. So the profit from making and selling 150 items would be $1,400. Okay, so that's putting together a lot of the things we've been covering in economics. There's 2 more economics examples that you can watch on the videos if you want more practice with that. They are linked in Moodle. Otherwise, have a great rest of your day. And that is the end for you of Calculus 1. So good luck on your future journeys. Maybe I'll see some of you in the summer class. Otherwise, have a great rest of your week here.